Hello, in this video we will examine how ClassWiz can be used to help students understand exponential models. Start by turning on the ClassWiz and setting it up. We're going to start using calculate mode in this video, so choose menu and number 1 for that purpose. An exponential growth model occurs when a quantity changes in a way that depends on its size. A good example of this is population growth, where a steady rate of change leads to increasing change as the population increases. Let's look at an example. The Malaysian population in 2010 was 28,334,135, according to a national census. The annual rate of growth of the population was around 1.5%. We'll store this value of 28,334,135 into memory A. So we use store and number A. You can see the pink A above there, so that we don't have to keep entering it all of the time. And just to show how that works, if we now tap alpha and A, we can see the value is recalled to the screen. So a mathematical model for Malaysia's population might assume that the growth rate stays constant at 1.5% per annum. So every year the model predicts that the population will increase by a factor of 1.015. So we multiply by 1.015 the value for A, the previous value, to see what the population will be in 2011. You can see that it's almost 29 million. In 2012, we need to press equals again to repeat the same command in ClassWiz and see in 2012 the population is a little bit over 29 million, and 2013, 2014, 2015, 2016. Every tap of the equals key repeats the previous command, which multiplies the previous command by 1.015. A more efficient way to describe this growth is to use a model with an exponent of 1.015. So let's see what that looks like. Alpha A times 1.015 to a power. So after 20 years, for example, the population would be predicted to be 38 million. In 2020, 10 years after the census, the population would be predicted to be 32.88 million, or almost 33 million people. It's important to keep in mind that this is a mathematical model, and it depends on the assumption that the growth rate stays the same. We could use this model to predict the size of the population in years to come, assuming there was no change in the growth rate. For example, we might like to wonder, when would the population be 40 million in Malaysia? And we can edit this command by tapping the left arrow key and backspace and change it. If we guessed, say, 30 years from now, 30 years from 2010, the population would be predicted to be 44 million. That's too much. So let's edit the command again and say we're looking for 40 million. What about 25 years? And that's a little bit too much, but only a little bit too much. So maybe we can try again and edit the command and say, what about 24 years? It's a little bit too much, but only just. So we might say 23 years would be the best prediction, and you can see that's a little bit less than 40 million. So after 23 years, the population is modelled to be almost 40 million, assuming that the growth rate stays the same over that period. Well, this is a useful way for students to begin exploring an exponential model. There are more efficient ways of doing so on ClassWiz. A good option is to use a table of values. So let's enter table mode with menu and number 9. And the function we have in mind is the mathematical model, which is still using our value for A. We've stored it and we haven't changed it. multiplied by 1.015, which is the predicted growth rate every year, to the power of x. It's an exponential function. So let's predict. We'll start with 0. That's a good idea to make sure that it predicts the value in 2010. And let's say we can have some other values. We can have up to 30 values altogether. So let's just go to 29 values, because the 0 is one value, in steps of 1. Each step now will represent a year. So tap equals again, and here is the result. You can see that ClassWiz shows in the table the results in exponential notation. But if you highlight the results with the cursor, we have the number showing at the bottom of the screen in normal decimal notation. If we scroll down, we'll firstly see that the first value is in fact the census value back in 2010. And we can see how the values change each year. Students could draw a graph of these, understand how the population was changing, and easily tell what we saw before, that the population is projected after 23 years to be close to 40 million, and in the after 24 years to be a little bit more than 40 million. We could, if we wanted, choose a value. We could change the x value and say, what if it was a little bit more than 23, a more fine prediction like maybe 23.4, and go back and see what result that's given us, and that's very close to 40 million. However, it would be unwise to be too precise with numbers here. Such accuracy is not appropriate when we're dealing with data of these kinds and we're making assumptions. Remember, the model relies on the assumptions entirely. So approximately 23 years would be a better answer than trying to give a very finely precise answer. And in this case, it is in fact unlikely over such a long period that the growth rate of the population would stay exactly the same. The same idea can be used to predict values that are not in the table, such as the population in 2050 when the value of x is 40. So we can change this value to 40 and see the population is very large. A very large population of more than 51 million people is predicted if the growth rate remains constant at 1.5% per annum. A feature of mathematical models is that they can be used to model events. In this case, different population models can be constructed by changing the function. For example, if Malaysia's population growth rate was assumed to be 1.3% and not 1.5% per annum, a change in the model will show fresh predictions. So how can we do that on ClassWiz? Here we would change our multiplier. Instead, delete that 5 and change it to a 3. And now we've changed the model to have a 1.3% growth rate. And we can have the same values and see what happens. And after 23 years, for example, the population is predicted to be only 38 million, where previously it was 40 million. Similarly, models can be compared with each other. For example, let's compare the original model with a model that has an annual growth rate of only 1.1%. First, we'll restore the original model. So change this 3 back to a 5. And we'll use the second table function, g at x, to model the population growth with 1.1% per annum. So it's a very similar looking model, 1.011 to the power x. And now we'll use the same values. And the first column now shows the model for a growth rate of 1.5%, and the second column shows the 1.1% model. So let's look down here. Say after 10 years, the original model predicts 32.8 million people, and the other model predicts only 31.6 million people. Each year the population in column 2 falls a little bit further behind the population in column 1. And if we go down a bit further, after 20 years, The first model has 37.5 million, and this one is only less than 35 million. The population models we have examined here are examples of exponential growth, but exponential models can also be helpful to understand the opposite kind of process, of decay. Radioactive decay is one example. Another example is depreciation, where the value of something declines each year. Let's consider briefly an example of depreciation. Computers are examples of things that depreciate quickly in value. Suppose that your computer depreciates by 20% per annum. So a computer purchased for $1,000 is assumed to decline in value by 20% each year. That is, each year it is worth only 80% of what it was worth the previous year. So an exponential model for this situation is, let's start with 1,000, the original value, and multiplied by 0.8 to the power of x. And we don't need this particular function. And let's see what happens to the value of our computer over a period of, say, 12 years. We start with 0, go to 12, and look at the results every 1 year. And to get our table of values, here it is. And as usual, we can scroll the table to see how the values change from year to year. So in the first year, the value is $1,000. A year later, it's declined to be worth only $800, 80% as much. The following year, it's $640, and we can see how the computer values depreciate over time. After 3 years, it's worth only a little more than half of what it was originally worth. Models for exponential decay are sometimes written differently with a negative exponent to make it clear that decay is involved. In this case, the reciprocal of 0.8 is 1.25, so a suitable model might be written with a negative exponent like this. So instead of 1.8, we have 1.25 to the power negative x, because multiplying by 0.8 is the same as dividing by 1.25. And here we see, we look at the values, they are in fact the same as they were previously. After 3 years, the value is declined to 512, and after 10 years, we can see that the depreciation model shows that the value of the computer is not much more than $100. So that's the end of our examples of exponential modelling. It's clear that students can explore exponential models efficiently with ClassWiz and solve some practical problems. They can change the parameters of the model and see their effects. You will find that Module 6 of the ClassWiz book also contains information on how ClassWiz can be used to deal with some exponential models, as well as detailed explanatory text which can be copied for students as well as teachers. The module includes some exercises to check efficient ClassWiz use, some examples of activities to suggest educationally valuable things to do, and some guidance for teachers. You can download this book freely from the Casio Worldwide Education website. Happy calculating!